In this particular standard 8.F.2, this is where we compare functions that are represented in different ways. Algebraically, like maybe given a function, graphically in terms of a graph, maybe given a table, or maybe sometimes just with context. As you can see in this particular problem, we have a table, we have a function, and we have a graph. And the question is, which of these has the largest slope, and then what is that slope? Well, let's start with the table. Remember, in terms of tables, it's as simple as finding the change in y over the change in x. So we can see here that the change in y, we're adding 4 to get from 5 to 9, and then the change in x, we're adding 4 to get from 0 to 4. And so the change in y is 4, the change in x is 4, so the table has a slope of 1. With a function, a linear function, not really doing any work there, so I can see that the slope is 2. And as far as the graph goes, I have to find a couple of perfect ordered pairs. So I see one there at 0, 1, and it looks like the next one is at 4, 4. So we have a rise of positive 3 to get from 1 to 4, and a run of 4 to get from 0 to 4. Remember, upward movement is a positive movement. Right movement is also a positive movement. And so the slope, or the rise over the run, is 3/4. So the question was, which of these has the largest? Well, clearly, that would be the equation. And then that particular slope happens to be a 2. So let me take off my writing here, select 2, or the equation, and put into, and we can see that that is correct. All right, continuing in the standard 8.F.2, where we are comparing functions in different ways. Here we have an equation, a graph, and a table, and the question is, which one has the largest rate of change? Well, remember, when we are finding the rate of change, we can, in some ways, think of the rate of change as the slope. So we can see for the equation, that's really easy. K equals 5m plus 5. The 5 of the 5m is the slope. And so we can see we have a slope of 5 there. The question is, which one has the largest one? As far as the graph goes, we need to find a couple of perfect ordered pairs. I see one there at the y-intercept. And it looks like maybe even one right there. So here we are rising 1 and running 1, so I can see that the slope is 1 from the graph. So clearly it's not the one with the largest. And as far as the table goes, we find the change in y. To go from 2 to 6, we have to add 4 over the change in the x values. To go from 0 to 1, we have to add 1. And so the change in y, or the change in the output over the change in the input, is 4. The question is, which one was the largest? Well, clearly it's that one, and the rate of change would be 5. Let me take off my writing here. So we have the equation, and that would be 5. Now, if you were asked for the smallest one, well, then that one would have been the graph. But we were asked for the largest one in this particular problem. All right, continuing with the standard 8.F.2, where we are comparing different functions. In this particular problem, we have a table, an equation, a graph, and some context here. So the question in this particular problem is, which one has the largest rate of change? Well, let's start with the table. And remember, to find the rate of change, or the slope, it's the change in the output over the change in the input. To go from 4 to 6, we have to add 2. To go from 0 to 2, we have to add 2. We really don't need to check any more than that. Change in output over the change in input is 1. As far as the equation goes, that's really easy. The rate of change would be 1/2. For the graph, we've got to find a couple of perfect ordered pairs here. So maybe one right there and one right there. And So we are rising 2 and we are running 1. Remember, slope can be thought of as the same thing as the rate of change. So we have rise of 2, run of 1. So we can see that the rate of change is 2 or 2 miles per hour in that particular problem. And then in the context, Demetrius is on a bike ride and he has already traveled 2 miles. That means that that is the initial value. And then he is now traveling at a constant rate of 5/2 miles per hour. So in the context, the rate of change is 5/2. Well, the question is, which one is the largest? Well, the table had a rate of change of 1. The equation had a rate of change of 1/2. The graph had a rate of change of 2. And the context has a rate of change of 5/2, which is really 2.5 or 2.5. So that means that it is the context which has the largest rate of change, and that happens to be 5/2. So let me take off my writing there. And this, of course, like many problems, rotates between, it could be the table, it might be the equation, it might be the graph, or it might be the context. Continuing with the standard 8.F.2, which is where we are comparing functions in different ways. Here we have a table, here we have an equation, and in this particular problem, we are trying to find the difference between the flat rate for plan B and the flat rate for plan A. Well, the first sentence above the answer box says the flat rate is defined as the monthly cost for the phone when 0 minutes are used. So this part right here. So that's really asking for what was the initial value. So the flat rate is what the initial value was or is, or you could think of it as the y-intercept. Well, the y-intercept in the table is found right there. When the time is 0 minutes, the cost is $20. And in terms of the equation, it is that value right there. So that has an initial value of $30. So the question is, what is the difference? In other words, we need to take those two values and we need to subtract them. So once again, the initial value in the table is b equals 20. From the context, it is b equals 30. And the difference between those two would, of course, be 30 minus 20, and that would be 10. Continuing with the standard 8.F.2, where we are comparing functions in different ways. In this particular problem, we are told that function A is a linear function, and some values of function A are in the table, and function B is also a linear function with a given x-intercept and y-intercept. So the first part of this, clearly, as you can see, we need to find the slope and the y-intercept, or the numeric value of the y-intercept. Sometimes that's referred to as the initial value. And then down below, we can answer some questions from that. So let's go ahead and do that. From the table, the slope, we find the change in y values. To go from 10 to 4, we have to subtract 6. Over the change in x values, to go from -1 to +2, we have to add 3. So the change in y values is -6. The change in x values is 3. And that, of course, is -2. Now, I'm going to go ahead over to function B and find the slope as well. So when we have a y-intercept of 1, that means technically we have an ordered pair found on that linear graph of 0, +1. And if the x-intercept is also +1, well, that would mean we would have another ordered pair that would be found on the graph of that linear function that would be at 1, 0. And so we can now use the slope formula, which remember is the second y value minus the first y value over the second x value minus the first x value. Now we could, of course, sketch a graph of those 2 points and utilize rise over run if we wanted to, but I prefer to go with this route. So the second y value is 0, and we're going to subtract from that the first y value, which is positive 1, over the second x value, which is the x value of the second ordered pair, which happens to be positive 1. And we're going to subtract from that the first x value, which happens to be the x value in the first ordered pair. And we get negative 1 over positive 1, which is negative 1. So we can see that the slope from those two pieces of information is negative 1. Okay, now, as far as the y-intercept goes, I'm going to take the easy one. Clearly, the y-intercept in the second piece of information, or function b, it's already right there for us. So that would be positive 1. As far as the table goes, the first place we should look is within the table. But I don't see a 0 comma something in our table. So we're going to have to do what I call filling in values or working backwards. So off to the side, I'm going to sketch the first 2 ordered pairs. Now, what I'm going to do is I'm going to leave some gaps here, because what I'm trying to do is I'm trying to work my way to, and I'm going to do a little bit of erasing right there. And because I'm taking that ordered pair, putting it in the table, and also that one right there. Okay? So we got to kind of work our way backwards to get to the y-intercept. Now, I could also work forwards also. Remember, we already know that our slope is negative 2. So what that means for us is that we have a change in y value of negative 2 for every change in x value of positive 1, because negative 2 over positive 1 is negative 2. Or we could see, to get from the x value from negative 1 to 0, we would have to add 1. So if we subtract 2 from 10, we have 8. Now already we are at our numeric value of the y-intercept. So if that ordered pair is not found in the table, then there are times where you have to utilize that sort of strategy. Okay, now I'm going to take all my writing off so that I can, and I'll fill in these blank areas, and then I'm going to be able to answer the other 2 parts of the question. So let me take those out, and we had negative 2, positive 8. We had a slope of negative 1, and a numeric value of the y-intercept of positive 1. Okay, so now regarding the y-intercept, this part right here, the very first part, the y-intercept of function A is equal to that of function B. That's not true. The y-intercept of function A is greater than the y-intercept of function B. That is true. Regarding the rate of change, the slope of function A is equal to function B. That's not true. The slope of function A is less than the slope of function B. That is true, because the slope of function A is negative 2, and the slope of function B is negative 1. And that's how we would deal with a problem like that. Continuing with the standard 8.F.2, where we are comparing functions in different ways. Here we have we're given a linear relationship of y equals 4x plus 2. So we know in this particular situation that the rate of change, or the slope, is 4. But we're asked to graph a linear relationship with a rate of change that is greater than the equation. So we can graph anything or any line in this particular problem that has a slope that is greater than 4. So I am going to take the easy way out, and maybe I'll graph, I don't know, y equals 5x plus 1, because that would be a linear equation or a linear function that has a slope of 5, and that happens to be greater than the slope found in the equation right there. So we'll start with a y-intercept of 1, and rise 5, run 1, and that would be correct. And I could have pretty much taken any slope or any y-intercept as long as the slope was larger than 4. Continuing with our standard 8.F.2, where we are comparing functions in different ways. Here we have a table, and then we're going to have to create a graph based upon the information found to the left of that. So Joseph and Claudia wrote down 2 different functions that have the same rate of change. So first of all, an example of 2 different functions that have the same rate of change might be y equals 2x plus 1 and y equals 2x minus 1. Those both have the same rate of change of 2, but they're different functions because they have different y-intercepts. So if you were to graph them, they would be lines that are parallel to each other, but they're not the same line, okay? So now Joseph's function is given by the table right here. So the first thing we're going to need to do is to figure out what Joseph's rate of change is, and then figure out what his y-intercept is, because Claudia would have a function that would have the same rate of change but has to be a different function. So let's first of all start with the slope. So just remember, slope is the change in y values. To go from -4 to -2, we have to add 2 to that. -4 plus 2 is -2. And to go from -1 to +1, we also are adding 2. So a change in y value over the change in x value. So we know that Joseph's function has a slope of 1. That means Claudia's rate of change or slope has to be also 1, because remember, they have the same rate of change. Now, we need to figure out what Joseph's y-intercept is. And the reason is because Claudia's has to be different. So we don't have the y-intercept found in our table, but clearly the y-intercept will be at 0, comma something. So I need to find the value halfway in between, basically -1 and 1, and then really halfway in between -4 and -2. But I could use the idea that we know the slope is 1, so we would have to be adding 1 to -4 to make -3. And then, of course, we added 1 right there to get from -1 to 0. So that means Joseph's y-intercept is -3. So Joseph's equation is y equals 1x or y equals x minus 3. So Claudia's equation that we graph has to have the same rate of change or the same slope, but a different y-intercept. So maybe, I don't know, y equals x minus 4. We don't really need to get overly complicated there. So let me go ahead and clear all this off and then graph y equals x minus 4. So we have a y-intercept of, remember, anything but -3 and the same rate of change, and submit that, and we can see that Claudia has the same rate of change but a different y-intercept, which means she has a different function than Joseph.